I want to switch gears a little bit and talk about how C# compiles. So when you think of how programming languages typically compile, you would often group them into two buckets. You would maybe have a statically compiled language or a just-in-time or JIT compiled language. And these languages often fall squarely into these buckets. However, C# just had to be different. And instead of picking one of them, it does both of them. Let's quickly compare static and just-in-time compilation. When we say we are statically compiling code, it means that all the code that is available gets compiled down to native or machine code when you press the proverbial build button in your IDE or you type in .NET build or something like that. Whereas with just-in-time compilation, we only compile the code down to native code right before execution of a line. And that is why it is called just-in-time compilation, because it literally is just in time. Both approaches have its merits and they have its drawbacks, but the biggest difference probably would be either performance or portability. Because you don't have a lot of overhead of having to compile code at runtime, static compilation typically results in faster code. If static compilation results in faster code, then why would you use JIT? Well, perhaps the best argument is because you are compiling code on the fly, you can target different architectures as necessary. So this allows you to run the same executables on different platforms. And as a result, that allows us to run C# and .NET on different platforms from the same intermediate language code. And more on that in a slide or two. To understand the .NET compilation process, this is about as deep as we're going to go with static and JIT compilation. It's probably also about as deep you're going to get from me. Let's take a look at what the compile stages look like. So when code written in a .NET language, perhaps called a CLI, Common Language Infrastructure Language, it's a specification that all .NET languages adhere to. When such a language is compiled, it does so in two main steps. First, after you write your high-level code in C#, VB.NET, F#, you press the compile button or you type .NET build into the terminal. And this statically compiles your code to something called intermediate language. This intermediate language code looks very much like code written in assembly. Once you execute your program, the runtime, the CLR, Common Language Runtime, takes that intermediate language code and jets it into native code for the machine that you're executing on. So for the Common Language Runtime, a comparison that is often made is to Java's Java Virtual Machine. And to an extent, that is valid. However, keep in mind that when people talk about the JVM, they often also mean the libraries within the JVM. In C#'s case, those libraries would be .NET and not the CLR. The CLR is part of .NET, but it is not the entirety of .NET. So on this screen, you see a simple program. Don't bother correcting any mathematical mistakes. It's just for educational purposes. This method accepts two parameters, both 64-bit floating points called doubles in C#, and it also returns a double. The two provided arguments are squared and summed before being returned out of the method. For example, if we were to call this method with an argument set of 3 and 4, then hopefully the outcome would be 52. So let's assume you fed this method to a compiler. The first step to executable code would be to compile this C# code to intermediate language. So now we're going to press that build button, type in .NET build, and step through the process going from C# to intermediate language. Sometimes you'll see intermediate language referred to as MSIL, Microsoft Intermediate Language, or CIL, Common Intermediate Language. For this talk, I'm going to keep using intermediate language. All CLI compliant languages compile down to intermediate language. And that allows us to target the same runtime with C#, VB.NET, F#, and more. Now here on this slide, you see the intermediate language representation of the Pythagoras method we saw before in high-level C#. If you are familiar with assembly programming, you may recognize some of these opcodes. When you distribute your C# application, this is what you're distributing. It is this intermediate language code that gets embedded into an executable type, often a DLL file. But it's not very important to know the internals of intermediate language. It's just good to know that it's there and what the output of your compilation step is. If you do want an almost line-by-line description of what this does, I would refer you to chapter 2 of my book. For now, let's move on. The code reflects the static compilation phase of C#. All this is done when you press build. It's done by the compiler ahead of time. But now we want to run this code. When we double-click our executable, launch our service, or invoke a DLL, the CLR, the Common Language Runtime, scans the file for any intermediate language code. When it finds this code, it will compile that code just in time to native code where necessary. So this means that code really isn't compiled until right before it's executed. And from that, we get that support for multiple platforms for the same codebase. Because processors and operating systems have a lot of different instruction sets, and we don't compile to all of those ahead of time, we can determine the correct instruction set at runtime and compile to that target. Now, unfortunately, it's quite tricky to nigh impossible to view the resulting native code. It would also just not be readable, and my machine's native code would differ from your machine's native code. So unless you've become fluent in your favorite controller's instruction set, it's a lost battle. So we've now seen static and JIT compilation. But why bother using both of them? After all, languages such as C++ get by with only static compilation, and they are multi-platform. Well, the rub is in the fact that typically languages like that tend to use compilers for different platforms. There may be a different compiler for Windows, Mac OS, Linux. Whilst when using a runtime like .NET or the JVM languages, you only have to use one compiler and rely on that compiler to compile to the correct target. That just gives us some flexibility in the platforms we develop for. Because we do compile down to intermediate language prior to native code, we can use multiple CLI compliant languages at the same time. Now that sounds a bit odd, but this allows us to call code written in languages such as VB.NET and F# and treat it as if it was C# code. A similar scenario can be seen with the JVM languages, where you can have interoperability between stuff like Java and Kotlin. Like I mentioned before, there is a downside to combining static and JIT compilation, and that is performance. This is mostly a JIT problem because we are waiting until the last minute to compile code. We incur that extra overhead. Code just runs slower when compiled just in time versus statically. And that's it for our tour through the .NET and C# compilation process. Like I said, if you want to dive deeper into this, I would suggest you check out my book. And besides that, there is an excellent book on the internals of the CLR. It's called CLR via C# and written by Jeffrey Richter. Now note that it doesn't deal with .NET Core and Core CLR, as that book came out before the release of .NET Core, but it still contains a lot of information, a lot of great information. The last section of this presentation. We've discussed the history and definitions of C#, .NET Framework, .NET Core, .NET 5. We looked at some ways to implement encapsulation and polymorphism in C#, and then we just looked at how we actually compile our code. In this section, I want to focus on 2.5 of my favorite pro tips. Now, that being said, what constitutes a pro tip very much depends on whether you already know the material or not. So that is the slight caveat here. First up is some fun with LINQ. LINQ stands for Language Integrated Query, and it is syntax inside C# that allows us to deal with collections in an almost functional programming way. LINQ is to C# as streams are to Java. They really serve a very similar purpose. And it can look a bit funky at first. There's no LINQ on the screen yet. But once you're used to using LINQ, you will find yourself using it quite often. And this section is really 2 tips in one, as we both look at the for each and where clause. Now, the basis of our exploration of the for each and where methods is this little code snippet that we saw earlier. If we zoom in a bit into the second half of this code snippet, we spot that for each loop, which in turn prints out details about all biscuits that are delicious. It is this for each loop that we are going to replace with a LINQ method call. The syntax for any LINQ method typically is the collection followed by the LINQ method, and the LINQ method usually accepts a lambda predicate alongside an expression. And this expression could be a single statement, or it can be an entire method body wrapped into curly braces. By replacing the for each loop with a LINQ for each method, our code is a little bit more condensed, and depending on your personal opinions, it may be easier to read, but maybe you prefer the previous one. This is somewhat of a trivial change that we made to the code. But once you start to combine for each methods with other LINQ methods, you can change some interesting things. So within this for each method, we have a method body, and we have here a conditional that checks whether a biscuit is delicious. If a biscuit is delicious, we print out its name and its serving size. Now, we were able to condense the for each loop a little bit by using a LINQ method, so perhaps we can do the same with this conditional check. Well, if we use the LINQ Where method, we may be able to say for this collection, select all elements where condition is X, where those are valid. So probably the most obvious attempt to implement where and for each together would be as you see in the slide. Now, unfortunately, this doesn't quite work. The where LINQ method returns a type of IEnumerable, whereas the for each method expects a type of list. Now, those are not compatible. And this incompatibility prohibits us from chaining the where and for each methods together like this. So until we find a solution for that, the best we can do is take that resulting IEnumerable type from the where method and just do a regular for each loop over it. Which is what you see on this slide. We just do a regular for each over the resulting IEnumerable collection coming out of the LINQ Where method. And this collection only contains the delicious biscuits. So we're good to print out the names and serving sizes for all elements. Now, I don't know about you, but I'm still a bit unhappy that we can't use both the LINQ for each and the LINQ Where methods in one chain. So perhaps we should just roll our own for each method that does work with IEnumerable collections. And that brings us to extension methods. C# allows you to define methods that operate on types rather than live in a specific instance of types or in a class that gets instantiated. For example, in the scenario outlined in the previous couple of slides, we could create an extension method called forEach that works with all IEnumerable types. And because extension methods are static, they can be called from anywhere. All we have to do is declare a static public method, preferably in a separate extension methods class, that says for type of X, which is for us an IEnumerable, of type T, a generic IEnumerable, where T will stand for biscuits during our code. Do this action for all elements in that IEnumerable. The weirdest part of this method signature is probably the this keyword. Yeah, that is what makes it an extension method. We are constraining this method to be called only on the type immediately following the this keyword. So in this case, this for each method can only be called on an IEnumerable, on a generic IEnumerable. We also pass in an instance of action of T. That's where our lambda predicate goes. The action class acts as a wrapper around our passed-in expression, and it is invoked on every element in the values of IEnumerable. So how would we go about calling this method then? Well, does that look familiar? It's the same code we saw a couple of slides ago. So where we try to use links for each method and we try to chain it with the where method. Now back then, the code did not compile because links for each method was incompatible with the given type. But this time around, it does. We are in fact calling R for each extension method. It's the extension method I just showed you. So extension methods can be a powerful tool to, well, extend functionalities of types. And that brings me to the close of this talk. I do have some suggested readings besides my book, Code Like a Pro in C#. These are some fantastic books that I highly recommend you check out. Two that I'll highlight are Clean Code by Robert Martin, which in my opinion is just the Bible of software development. And there is C# in Depth, which is an absolutely fantastic book that is also published by Manning. So with that, thank you for listening. Feel free to connect with me on LinkedIn, visit my website, visit the Manning page.